Pluto, a distant and mysterious dwarf planet, was once considered a full member of our solar system's planetary family. A recent surprising announcement by leading astrophysicists Neil deGrasse Tyson and Michio Kaku has put Pluto back in the spotlight with a shocking discovery. They suggest that the icy world is on a possible collision course with Neptune. But how could this happen, and what would be the consequences of such a massive event? Are we witnessing a rare astronomical phenomenon, or is there more to the impending cosmic collision? Join us as we explore the possibility of a Pluto-Neptune collision. Pluto, a former planet, has been relegated to dwarf planet status due in part to its unusual orbit, but it still remains a subject of fascination and study in astronomy. Recent predictions by leading scientists place Pluto's orbit dangerously close to that of Neptune. Neil deGrasse Tyson and Michio Kaku both raised the red flag about the possibility of a dangerous collision between the two planets, which could even threaten Earth. But how could such an event be possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a whopping 248 years to complete one revolution, meaning that it has not yet completed a full revolution since its discovery in 1930. Adding to its interest is Pluto's highly elliptical orbit, which deviates significantly from the nearly circular orbits of the major planets. Pluto's orbit is also tilted 17 degrees relative to the ecliptic, making it much steeper than the other planets. This tilt and elliptical nature adds complexity to orbital models. One of the most interesting aspects of Pluto's orbit is its intersection with Neptune. During each orbit, Pluto actually gets closer to the Sun than Neptune does, which is far from what you would expect for its position in the solar system. This leads to a natural question. Why didn't Pluto collide with Neptune? The answer lies in the gravitational influence of another planet. The study of Pluto's orbit began almost immediately after its discovery. Initially, astronomers tried to understand its unique trajectory. Unlike other planets whose orbits are relatively close to the ecliptic, Pluto's orbit is notable for its steep inclination and elliptical shape. The mystery deepened when it was discovered that Pluto's orbit actually intersects Neptune's orbit. Despite this complexity, the stability of Pluto's orbit demonstrates the complexity of cosmic dynamics. The cosmic three-body problem, which understands how three bodies, Pluto, Neptune, and the Sun interact with each other's gravity, helps explain this. The azimuth oscillation, the latitudinal oscillation, and the VZLK oscillation are part of this puzzle. Azimuth wobble means that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees from Neptune, providing a spatial separation that prevents collisions. Latitudinal wobble refers to the vertical movement of a celestial body in its orbit. In Pluto's case, this means that it is well above the orbital plane when approaching Neptune or another giant planet, adding another layer of protection. Named after scientists who study how gravity interacts in space, the VZLK wobble better explains Pluto's unusual path. Although Pluto's orbit appears unstable, the wobble helps Pluto move smoothly over long periods of time. This shows that even though objects in the universe appear rough and random, some patterns and rules maintain order. These components combine to keep Pluto's orbit stable and prevent it from colliding with Neptune. Numerical simulations from the late 1980s showed that despite these stabilizing properties, Pluto's orbit is technically chaotic. Small deviations from initial conditions can lead to significant differences over millions of years. However, Pluto's unique orbital features have been found to be stable for incredibly long periods of time, effectively preventing chaos. Recent computer models have shown how the major planets Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. There is a special connection between Pluto and Neptune. For every 2 orbits Pluto makes around the Sun, Neptune makes 3. This synchronization helps keep Pluto's orbit stable. Jupiter's gravity also plays a role in keeping Pluto stable, and Saturn has a small but beneficial influence. These planets work together to ensure that Pluto continues its journey safely through space. These gravitational interactions are necessary to maintain order in the solar system. Without them, the solar system would be much more chaotic, and bodies like Pluto could potentially collide with other bodies or be kicked out of their stable orbits. Understanding Pluto's orbit is particularly important given recent concerns about a possible collision with Neptune. It gives us a clearer picture of the dynamic nature of the solar system and shows how seemingly unstable orbits can reach equilibrium through complex gravitational forces. Studying Pluto's orbit provides insight into the unpredictable nature of celestial bodies. The concept of orbital chaos, where small changes in a celestial body's position can have large effects on its long-term path, is clearly illustrated in the case of Pluto. Computer simulations have played a key role in studying these dynamics, allowing scientists to test whether small changes in initial conditions can fundamentally change Pluto's orbit over millions of years. Despite this chaos, Pluto's orbit remains stable for billions of years, showing that even unstable paths can exhibit forms of long-term order. Predicting cosmic events, especially those involving chaotic orbits like Pluto's, is a major challenge. Simulations depend on the accuracy of initial conditions, and even small errors can lead to completely different results, making accurate predictions difficult. This unpredictability reminds us that despite the great progress we have made in understanding the universe, our knowledge of it is still limited. The gravitational influence of the giant planets on Pluto provides valuable information about the broader dynamics of the solar system and shows how the positions of each planet affect the stability of the others. So why are leading astrophysicists only now raising concerns about the possibility of a Pluto-Neptune collision? Neil deGrasse Tyson, a prominent astrophysicist known for his contributions to the reclassification of Pluto, offers a unique perspective. He sees the reclassification not as a downgrade, but as an adaptation to our expanded understanding of the solar system. Tyson believes that studying the intricacies of orbits like Pluto can teach us more about the universe, and that our fascination with the unknown drives the field of astronomy. Theoretical physicist Michio Kaku emphasizes the need to study the broader implications of our knowledge of Pluto's orbit. He advocates investing in space research to prepare for future risks that could arise from celestial interactions. He also emphasizes the role of advanced technology in understanding and mitigating risks associated with cosmic events. The potential collision of Pluto and Neptune is not just an astronomical curiosity, but a reminder of the dynamic and unpredictable nature of the universe. It forces us to think about the fragility of celestial dynamics and the potential consequences of perturbations in the orbits of distant worlds. As scientists continue to improve their models and simulations, they are opening up new possibilities for understanding the ever-changing nature of the universe. The study of Pluto's orbit serves as a springboard for a broader discussion about the need for constant vigilance in space exploration and celestial observation. Looking to the future, new technologies will undoubtedly expand our research capabilities. Missions like NASA's New Horizons, which flew by Pluto in 2015, have already provided unprecedented data on the dwarf planet, its moons, and its geological features. The mission's results have revealed a complex landscape with icy mountains, vast plains, and even cryovolcanoes, challenging long-held assumptions and broadening our understanding of the geological activity of the outer solar system. In conclusion, the discussion of the possibility of a Pluto-Neptune collision highlights the complex dance of our solar system's celestial bodies. The interplay of chaos and stability in Pluto's orbit is evidence of the complex structure of our cosmic neighbor, where each body plays a role in maintaining balance. Whether a collision will occur remains an open question, but it serves as a reminder of the vast and ever-changing nature of the universe we live in. As we continue to explore the universe, its mysteries call us to discover the wonders that lie beyond our own planet, and the stories of Pluto, Neptune, and other celestial bodies guide our quest for understanding. The dance of the planets will continue, inspiring excitement and wonder that shape humanity's journey into the depths of space.